So hello everybody, welcome to our monthly seminar. So today we have the pleasure to have Mateus Pelicer talking to us about magnetic fields and compact stars. So let me introduce our speaker from today. So Mateus got his bachelor in physics from the State University of Maringá, got the master from the Federal University of Santa Catarina in high energy physics, and now he's doing his PhD in the Federal University of Santa Catarina in nuclear physics. He works with Deborah Menezes, and he will talk about this subject to us today. Thank you very much, Mateus, for accepting the invitation. So the microphone is yours.
Okay, thank you, Anna. Thank you for the invitation, and thank you, Deborah, for the indication. And thanks to everyone who is taking some of their time to hear me. I hope you can learn something today, and I hope it's entertaining. So I tried to make the presentation a bit brief and pedagogical, so I hope everyone can enjoy and take something with them after it. Okay, so I'm going to talk about magnetic fields in compact stars. And of course, I'm going to start with the usual diagram of stellar evolution, where the neutron star is the final end of the stellar evolution over here. Can you guys see my mouse?
Yes.
Yeah, okay.
Yes, I can see mouse.
Okay, so we have the neutron star as the final evolution. So we start with a nebula. This nebula usually clumps up due to the gravitational attraction. And if it becomes a high mass star, by this I mean that it has more than 8 solar masses, it's going to evolve in the main sequence to a red supergiant. And when the fuel to produce nuclear fusion ends, the outer layers are going to be expelled in an explosion, and the core, which is usually iron, is going to form a compact star, which is a neutron star. And in this process of the supernova becoming, of this red supergiants exploding in a supernova and becoming a neutron star, we have a lot of changes occurring. So the central density in the star is usually of the order of 10 to the 6 when it's a red supergiant. And then after the supernova explosion, this increases by almost 9 orders of magnitude. So it can become 10 to the 15 grams per centimeter cubic. And this is equivalent to about 1 Fermi to the -3, which is around 10 times the saturation density of nuclei. So my PhD is in nuclear physics, so I don't know what's the background of everybody, so I'm going to try to explain any terms that I use in nuclear physics. So the saturation density of nuclei is the average density of a nuclei, the nucleus of a nuclei. So it's usually 0.16 Fermi to the -3. And this neutron star will have a core which has a central density around 1 Fermi to the -3, which is this 10 to the 15. And when the star explodes in a supernova, there are two things that ideally would be conserved, and this is angular momentum and the flux of magnetic fields. So the radius of the star is going to decrease by many orders of magnitude. So a neutron star usually has a radius of 10 kilometers, say 8 to 16, something like that. So it's really, really small. It's something we can walk in one day. And the predecessor star, the star that gives rise to the compact star, usually has a radius of thousands of kilometers. So due to this conservation of angular momentum and magnetic flux, the magnetic field of the neutron star is going to be really, really huge. So it's usually of the order of 10 to the 9 up to 10 to the 13 Gauss. in a usual pulsar. And it's going to spin really, really fast, usually with periods ranging from milliseconds to a few seconds. So every second or every milliseconds, the star will make one rotation. And these are really, really high magnetic fields. And these magnetic fields can actually be increased if the electrons suffer Pauli paramagnetization. So if they all align up their spin, this can lead to a 9 times increase in the magnetic fields. And these neutron stars, they were discovered by Jocelyn Bell and her supervisor, Hewish, and she was injustice in the Nobel Prize, but yeah, that's it. In 1969, with this really huge antenna. And the pulsars that they used to capture or to measure were radio pulsars. So this is the standard pulsars that we have. And radio pulsars are usually powered by their rotation energy. So, but they usually spin down as time passes because they translate their rotational energy into the radiation that we can measure. And then we have X-ray pulsars, and these are usually powered by accretion. So they're in binary systems most of the times. And since they turn the hot infalling matter into radiation, they can either spin up or down. They can also accelerate as time passes. And we have also anomalous X-ray pulsars. So they don't have a frequency, let's say a periodic rotation, not a periodic rotation. They don't have a periodic pulsing like the X-ray pulsars. And we have also the gamma ray pulsars. And these two categories, they are thought to be magnetars. And the main difference between the radio and X-ray pulsars and the magnetars is that the first ones, they have surface magnetic fields up to 10 to the 12 Gauss. And the magnetars have a surface magnetic field between 10 to the 13 and 10 to the 15 Gauss. And this is a really extreme magnetic field. I think it's higher than anything else that we have in the universe, at least today. And in the magnetars, they are thought to be powered by the magnetic field's energy, not by rotation or by accretion. So they're really exotic objects. And the neutron stars, they are usually modeled in a very simple manner. In the very large scale that we're talking about, we usually can model them as a rotating dipole. And this is because the dipole is the component of the magnetic field that decays more slowly. So since we see the neutron star from very, very far away, the dipole component is going to be dominant. And this dipole approximation, the calculations involved in this dipole approximation, they show that a few properties are in place. So the star is going to slow down from radiation emission in this dipole approximation. And also, since the magnetic field is really high and the rotation is very fast, there will be an electric field that is created at the poles of the star, the magnetic poles of the star. And this electric potential is going to accelerate the electrons and the protons that are in the surface of the star. And this will create a plasma, which is a plasma in the magnetosphere of the star. And this accelerating plasma will co-rotate with the star within this light cylinder. So in this picture over here, you see the field lines of the magnetic fields. So we have a rotating neutron star. And we have the closed field lines over here on the right. And then we have a vertical bar over here. So this vertical bar is what determines the radius where the magnetosphere, the plasma in the magnetosphere can co-rotate with the star. So beyond this light cylinder radius, the particles would have to move faster than light to accompany the star in the rotation. So the magnetosphere should be only this big. So within this light cylinder, the electric potential will accelerate the co-rotating plasma, and this will make the radiation that we see from the bursts. At least this is a very simplified picture. The exact mechanism of these bursts is not really well known, but this is an ideal situation, let's say. And another important property that will occur, another event that will occur in these electric fields is photosplitting. So the magnetic fields in the magnetars, they are actually higher than the critical magnetic fields of the electron. And because of this, it's possible for the spontaneous creation of electron-positron pairs. So this also has to be accounted when you're when you are calculating the spectra of the electron that we are going to measure. Okay. Of course, there are other effects of the magnetic fields. Oops. So the electrons, they are quantized. And this is because in the transverse direction to the magnetic fields, the Landau levels will... sorry, there's someone with the mic open. If you could close, please. Thank you. Okay. Okay, so the electrons will be quantized in the plane parallel to the transverse to the magnetic fields. And because of this, the synchrotron radiation that we measure on Earth will be not continuous, it will be discrete. And this allows us to measure the particle level, the electron levels, and get some properties of the magnetosphere. So there will occur synchrotron radiation and absorption. The spin changing processes will be less likely to occur because the magnetic fields will prefer to maintain the spin at a certain direction. In this case, down for the negatively charged particles and up for the positively charged ones. It will affect, of course, the spectrum of the emitted radiation. It will affect the internal structure of the neutron star and its shape. And it can also modify the beta equilibrium in the inner crust and the equation of state in these regions. Okay. So in this dipole approximation of the magnetic fields that I have mentioned, it's possible to relate the surface magnetic fields to the periods of the star and to the derivative of the periods. So the relation is given by this equation over here on the right. So I over here is the moments of inertia of the star, P and P dots are the periods and its derivative, and these are 0 is the radius of the star. And so over here on the left, we have a diagram.
Can I ask a question?
Yes, of course.
When you say a dipole approximation, I mean, if you want to go higher orders, would be just quadrupole and so on.
Yes.
Okay.
Yes. Okay. Okay, so over here on the left, we have a picture where the y-axis is the periods derivative and the x-axis is the periods. And it's possible to construct over here lines of constant magnetic fields. So here, for example, we have a line of 10 to the 14 Gauss magnetic fields. So here you can see the population of magnetars, which are the soft gamma ray emitters and the anomalous X-ray pulsars. Then we have the radio quiets. Oops, sorry. Then we have over here the binaries, which are the X-ray pulsars. So they're below the spin-up line because they can spin up due to their accretion of matter. So these are the only ones that not the only ones, but they are the bigger population of spin-up pulsars over here. And then we have the radio pulsars, which are the higher population over here. And you can see that they are in the range of 10 to the 12 to 10 to the 11 Gauss, more or less. Okay, so this is a very good way to measure the magnetic field of the star because we only need the periods and the periods derivative, which I don't want to say it's a simple measurement because of course it's not, but it's simple enough to get these two quantities and the radius to have an estimate for these magnetic fields. So over here on the right, you have another picture for now we have the surface magnetic fields as a function of the periods. And we can see that the magnetars, they are clumped in a region of high rotation periods and very high magnetic fields. So the magnetars, they will also rotate slow, they will always rotate very slowly with a period between 2 and 12 seconds. And they will have a spin periods of the order of 10 to the minus 10 to 10 to the minus 13. And they have a persistent luminosity. So because they are powered by the magnetic fields, their luminosity occurs in a more constant way than the other pulsars. And it's also many, many orders of magnitudes larger because the rotation and the accretion energies, they are not sufficient to reach these energies over here, 10 to the 13 and 10 to the 36. Okay, so let's go further. Okay, something to mention over here, I think, is there was a discovery in the last 10 years of a soft gamma ray repeater. I don't recall the number. I think it's 0404 something. I don't know. And this soft gamma ray repeater, they measure the magnetic fields in this manner from the periods and from the periods derivative. And they obtained a value of 10 to the 12. So it was a soft gamma ray repeater. So in principle, it would be a magnetar, but it had a very low magnetic fields in the order of 10 to the 12. And they actually measured a proton, how do you say this? Resonance from, they measured the resonance energy of a proton scattering. And from this resonance, it's also possible to infer the magnetic fields of the star. And there was a discrepancy because from the resonance, the inferred magnetic field was 10 to the 14 Gauss, something of this order. So there was 2 orders of magnitudes difference in the estimated magnetic fields. And this has gotten a few people rethinking this dipole approximation to measure the magnetic fields, or maybe the calculation of the resonance in the neutron star. And honestly, I don't know how people have solved this problem. I have read just one paper where some guy has included a plasma in a rotator with a magnetic fields, and he was able to explain this discrepancy, but I'm not an expert on this subject, and I just thought I would mention it if anyone is interested in looking it up, because I think it was an interesting problem, an open problem in the last few years. Okay, so let's go inside the star now. So after the magnetosphere, we have the crust. So the crust is not formed with the neutron star because in its formation, the star is very, very hot. So it's completely superfluid and superfluid and a superconductor. But after it cools down, the crust will start forming a Coulomb lattice with nucleons. So in the beginning of the crust, we have the usual shapes of nucleons that we know. So they have these spherical shapes over here. And as we go more deeply into the neutron star, the competition between the Coulomb and the nuclear energy will become, the Coulomb and the nuclear energy will become comparable. So there will be a competition between these 2 energies. And because of this, the usual spherical shape of the nuclei can change into this amorphous phase, the pasta. So the ideal shapes that we usually consider to study the pasta phase are these cylindrical or slab-like shapes. And then in pink over here are the inverted pasta. So instead of having the dense nuclei over here, instead of having a dense nuclei surrounded by a neutron gas, we are going to have like bubbles of the gas surrounded by this very dense nuclei, which is the inverted pasta. And I'm talking about this because the pasta is believed to be very important in the thermal and the magnetic evolution of the star. And I'm going to talk about this a bit, but I also want to mention that it's probably a very important in giant flares in soft gamma ray repeaters. And this is because there is a competition between the crustal and the magnetic stress. And when the magnetic stress becomes too much for the crust to endure, it's going to break the crust and a giant flare will be released. Uh, I don't think this is a closed discussion, but this is what is believed to occur in for the giant flare. Okay. So I think I also want to talk about this very important paper by Pons. So this was published in Nature in 2013. And he wanted to answer a question over here. And he asked, where are the X-ray pulsars, the isolated X-ray pulsars with periods larger than 12 seconds? Because in this uh, picture over here on the right, we see that the binary X-ray pulsars, they can go over to up to 100, almost 1,000 seconds in periods. But the isolated pulsars, they do not. They usually stop at 12 milliseconds. And he argues that there is not a reason to believe that it's a selection of our measurements. So our measurements are not selecting the X-ray pulsars that have a slow period, like it occurs with the radio pulsars, because the radio pulsars, they have a luminescence that is directly related to the rotation periods. So as the star slows down, we cannot see it anymore. But with the X-ray pulsars, this should not happen. And he tries to explain why this is so. And what he argues is that if in the crust we have a very high impurity, so by this I mean there is a very heterogeneous distribution of proton charges. So all of these nuclei over here, the pasta and the spherical, they are coexisting with different proton numbers. And if they also are very amorphous, so they don't have any specified shape and the different shapes coexist, then we are going to have a high impurity parameter in the crust. And this is going to increase the resistivity of the star. And if the resistivity of the star is increased, or the conductivity is decreased, then it's going to alter the evolution of the magnetic fields. And then he makes a simulation of how it would occur. And what happens is that after about 10 to the 5 years of the star existence, the magnetic field is going to have a very steep descent. So over here, for example, in the first picture over here below, we have a magnetic fields of 10 to the 14 Gauss disorder. And then after 10 to the 5 years, the magnetic fields decays to 10 to the 12 seconds. And this, of course, since there is a relation between the magnetic fields and the spin periods.
What are the different curves? The different colors?
Sorry, can you repeat?
What are the different colors?
Of course, sorry. So over here on the upper parts, he tried modeling the impurity parameter of the crust. So he could not calculate how impure was the crust. So he just guessed a few values and a density dependence for these values. So here the first picture, we have the impurity. So in red, we have a high impurity throughout the entire crust. In blue, we have a high impurity only after we enter the inner crust of the star. In green, we have the same, but with a slightly smaller impurity parameter. And the yellow over here is a very low impurity parameter. And then he tries, so these are different impurity parameters that he modeled. And then we have how this impacts the resistivity over here on the second picture. And then below are the different curves for the different impurities that he modeled. So we see that when the impurity parameter is really low, so this yellow curve, then there is not this steep descent of the magnetic fields. But for this blue curve, this high blue curve over here, we can see that there is a very steep descendance over here. So in less than 1,000, well, less than 1 order of magnitudes of difference over here, there is a complete fall down of the fields. Okay. So I think this is really interesting because this is a way that we can get some insights on the inner crust of the neutron star just by measuring the evolution of the magnetic fields. And in this other paper by Horwitz, Barry and collaborators, they have applied the same reasoning of Pons on this paper. So they also modeled the defects of the inner crust, but this time they have actually calculated the transported coefficients, and then they used this impurity parameter in an ad hoc manner to, let's say, scale these transport coefficients. So it's like they removed a term proportional to this impurity parameter, and they have made then these plots over here. So, well, the conductivity, which is lowered by the high impurity parameter, is directly related to the thermal conductivity. So instead of trying to model the magnetic fields and the magnetic evolution, he tried to model the thermal evolution of the star. So here in the this full line, let me remember if it is the yes. So the dashed line is the standards calculation of the thermal evolution, and the full line is the calculation considering the impurity parameter. So we can see that there is the full curve describes a little better the points, I would argue, because this point below over here is right on point, and the other ones are really close to it, though I think it's open to debates. Oops. Okay. And one paper that me, Deborah, and a few other collaborators have published, we have actually calculated this impurity parameter. So I'll just talk about this black curve over here. So this picture on the right. And we find that as we go deeper inside the crust, this impurity parameter actually becomes of the order expected in these gases that Pons and Horowitz made. So he said that the impurity is indeed of the order of 100, which is the same gas that they made. Okay. Another important study, I think, with the crust and the magnetic fields was this one made by Wang, Li, Feng, Pais, and Providencia. And what they did was put the magnetic fields with a relativistic mean fields model and see how the appearance of the pasta would change. And they have found that if we try to see where the pasta appears when there is a very high magnetic field, there will not be a simple evolution, let's say a linear evolution of the pasta structures. So a linear evolution, I mean, we usually go from spheres to rods, then from rods to slabs, and then to the inverted slabs, and then to the inverted tubes and bubbles. But in her case, we have the spheres over here, then we have the rods, then the slabs. In this blue case, which is the highest magnetic fields, this is about 10 to the 17 Gauss, if I'm not mistaken. So we have the slabs, and then we have a bit of homogeneous matter, so we don't have pasta over here. And then we go back to the droplets, and the rods and the slabs appear again. And then we have the tubes and the bubbles. So there are disconnected spinodal regions where the pasta appears. And this is true for all the different magnetic fields that they applied. And this is really interesting because it implies that the crust is disconnected. So we have two parts of the crust. And also there is a much larger pressure at the crust-core transition because it occurs at a much higher density, so much deeper inside the star. Okay. So now let's move to the core. So the core is really a mystery. There could be a number of things in the core of the neutron star. So we can have exotic particles like the hyperons and the delta particles appearing over there. We can have only superconducting protons and superfluid neutrons, and this will alter the transport properties of the star and thus the magnetic field evolution. We can have pion condensates, we can have a quark-hadron transition, we can have color flavor locking, and this is when there is a one-to-one correspondence between the color and the flavor of the quarks. But I'm not going to talk about all of this because, well, I'm not, I think, suited to talk about it all. But I have worked with both exotic particles and the quark-hadron transition, so I'm going to talk a little bit about that. So the exotic particles, let's say the non-exotic particles are the usual protons and neutrons. But since inside the neutron star, we are at very high energies because of the high densities. So the particles are in a Fermi sea with a very high energy. Because of that, it's possible for these particles to spontaneously transition into different ones. So instead of just protons and neutrons, we can have the hyperons. So we have the sigma family, the lambda hyperon, and the cascade hyperons, and they might appear in the star. And then we have the excitations of the protons and neutrons, which are the delta particles. So they are so the hyperons, they are made of strange quarks. So they have usually one strange quark and up and down, or two strange quarks and one more up or one more down particle. And then we have also the excitations of the hyperons, but these are very massive. So I have never seen anyone studying if they could show up in the star. But given that the delta particles already show up at very high densities, I think it would not be, they would not be expected in the star, unless from some unknown physical mechanism. So over here on the right is a picture of a paper we have published, Deborah, me, Kawan, and a few other collaborators. Oops. Okay. So we have used a relativistic mean fields model, and over here on the upper panels are the density of the particles when there is no magnetic fields. And we can see that we have the protons, neutrons, electrons, muons, and then we have the lambda hyperon, and we have the delta minus and the delta zero particle showing up. And this is for a certain choice of couplings for the deltas. So the couplings of the deltas are not very well known. So we have to make a guess that they are close to the nucleons because of some experimental constraints we have. So they're not exactly known, but we have an idea of which range it should be. So we choose two different couplings for the deltas, and the same particles appear in both cases, though in different densities. And in the down panel, we actually added the magnetic fields, and we can see that a lot more particles appear. So at the low densities, the charged particles are very favored. So we have a very much higher density of charged particles at low densities. And when we go to the core of the star, we see that we don't have only the delta zero baryon appearing, but we also have the delta plus, the delta plus plus over here. And it does not appear in the case of a different coupling. So we have shown that this is very model dependent. So it's possible that these exotic particles appear in the core of the star, but it's really going to depend on which are the real couplings of these nucleons. Yes. Okay, so this other picture over here, it was made using the LOREN. The LOREN is an application, a computational application, where you can feed an equation of states for nuclear physics, and you can feed a central magnetic field, and it will calculate the magnetic field throughout the star from the equation of states and from the central magnetic fields. This is one of the possible uses of Loren, and this is how we work it in this paper. But I think there are other ways to use it as well. So this is a mass radius diagram, and the full curves over here were calculated without the magnetic fields. Then these dashed curves, they are the mass radius diagram with a central magnetic field of 5 times 10 to the 17 Gauss. So a very high magnetic field. And then these dotted curves, they are with a central magnetic field of 10 to the 18 Gauss. And I was talking that the magnetic field should be of the order 10 to the 13 to 10 to the 15 in magnetars, but that's only on the surface. So from the video theorem, we actually expect that in the core of the neutron star, the magnetic field is much higher than that. So three orders of 10 to the 18 Gauss are usually expected. So we can see that the maximum mass of the neutron star is not very affected by the presence or not of the magnetic fields. And this is because the magnetic field will induce a Lorentz force. And this Lorentz force is going to be much more important or pronounced at low densities. So the main difference occurs at the low mass stars. So below, say, well, let's say high radius stars. I think it's more appropriate. So you can see that the equatorial radius of a magnetized star will be much larger. So the star is going to be deformed. It's going to be achatada, let's say, squeezed. The star is going to be squeezed. So the equatorial radius is going to be much larger when the magnetic field is present. And with Loren, it's also possible to calculate the poles of the expansion. So the full curve over here on the left, we have the profile of the magnetic fields inside the star for different poles. So these full curves over here are for the L equals 0. Then the dashed ones are for L equal 2. The full / dashed, the full dashed curves are for the L equal 4, and then the dotted curves are for the L equal 6 expansion over here. And of course, the L equal 0 is the dominant one up to the crust, more or less. Then the dipolar field becomes very important over here, the L equal 2 term, and it's the case as we go further away from the center of the star. So this was really interesting to make. And we have made this with 2 relativistic models. So we did this with the L3 omega rho, which satisfies all the astrophysical properties that we know of maximum mass, the LIGO and Virgo data we have. And we have also used the chiral mean fields model, which is based on the sigma model. And in this model, the masses of the nucleons, they're not altered by the medium, but they are completely generated from the medium. So it has less free parameters for the mass, but it has a lot more mesons. So we actually end up with quite a few parameters. Okay, and then on the right, we have the full magnetic, the L equals 0 magnetic field. So we have the dominant term for different angles in the star. So this full curve over here is for theta equals 0. So it's in the direction of the poles. And then we have this dashed curve at an angle of pi over 4, so 45 degrees. And the dotted curve at 90 degrees. So it's the azimuthal parts, the plane transverse to the poles. And we can see that transversely to the poles, the decay is much faster than in the region parallel. Okay, and we did this for both the relativistic mean fields model and the CMF for these 2 mean fields models. And we can see that the difference of adding the delta particles, these exotic particles, is only really visible within this first model. in the CMF, there is very little difference. And the reason for that is that it's, well, I don't have a picture for the particle densities of the CMF model in here, but the delta particles appear at much higher densities in that model. So that's the reason it's that the delta particles do not really alter the magnetic fields. And another paper we have worked on was regarding phase transitions. So we believe that due to the very high energies, it's possible that a transition from the hadronic phase to the quark phase is possible. And because of that, this quark phase can appear both in So the quark phase can appear both in scatterings of heavy nuclei, heavy ions, as well as in the neutron star. The difference is that the heavy ions, they are usually in the high temperature region over here. And the neutron star, we are usually interested in the low temperature and high chemical potential region. And we have used this vector MIT bag model. So it's just the MIT model. So usually we have the bag model, a free Dirac Lagrangian, and we add these bag parameters so that it takes the role of a confining parameter, so that the quarks are confined inside the nuclei. And we have taken a model where people have added this repulsive interaction. So we have another meson over here where with which the quarks interacts. Okay. And so we expect the phase transition to occur when the pressure of the quarks become larger than the pressure of the hadron phase. So this red part over here is the hadronic phase, and then we have the transition for a different set of parameters. So this black curve is just for the bag, just with the bag, so we don't have the repulsive interaction. And then if we add repulsion, we can see this dashed line in purple over here. And this repulsion is going to decrease or soften the equation of state. So you're going to have a smaller pressure and thus a higher chemical potential and pressure for the transition. And then we can add also this self-interaction of the meson, and this will stiffen the equation of states and make the transition to a bit slower of a chemical potential and pressure. And what we did in this paper was try to study how the magnetic field would modify the point of the phase transition. And we have done this using two approximations that should be mentioned because they're really important. And the first one is flavor conservation. So usually people, when they're studying phase transitions, they assume that the hadronic phase is in beta equilibrium. And that makes sense because the star should achieve beta equilibrium after a while, after it's created. And they also assume that the quark phase is in beta equilibrium. But the time scale of the strong interaction is much smaller than the time scale of the electron-weak interaction. So the phase transition occurs due to the strong interactions. So it's going to occur very fast because of the small time scale of the interaction. So it's not going to, we are not going to have enough time for the beta equilibrium to settle in the quark phase. And so we are going to assume that let's say the hadronic phase pops. So we no longer have let's say a bag. Let's say a bag containing the quarks. They are now free to move, but the quarks are not yet in beta equilibrium. So this is why we assume flavor conservation instead of beta equilibrium in the quark phase, because of this difference of time scales. And we also use the chaotic magnetic fields approximation. And this is because in magnetized matter, we don't have a single pressure. So we have an anisotropic pressure. So the pressure is going to be different in the parallel and in the perpendicular directions to the magnetic fields. So we can't just say that the pressure of the hadron phase is equal to the pressure of the quark phase, as is usual in thermodynamics to consider phase transitions. So this chaotic fields approximation says that if at low scales the particles move really fast and in a chaotic manner, it's possible to approximate the pressure as isotropic, at least at the very small scales. And of course, since the neutron star is a pulsar and it has a very well-aligned magnetic field, this might not be the best approximation for compact stars, but we also have to remember that the magnetic field is very dynamic. It breaks, it reconnects. So at very small scales, this might actually be a decent approximation. Though in supernova explosions, it would be much better because of their things are really chaotic. But this is the way we found to make this work. So we have used this chaotic field approximation. And in these pictures, I have the full curve for the point of the phase transition with a magnetic field. And then the dashed curve is for the point of the phase transition without the magnetic fields. And this is all at 0 temperature. And the y-axis is the chemical potential, and the x-axis in the first picture is the Baggy parameter. So it's this confining parameter in the Lagrangian over here. And we see that the magnetic field is more important at smaller values of the bag. And this is because at smaller values of the bag, the density is also lower. So that's the place where we see that the particles over here, the charged particles, are more influenced by the magnetic fields. So we are going to have a bigger impact. So if this phase transition occurs at lower chemical potentials, it's certainly impacted by the magnetic fields. It's going to occur a little earlier. And then we have another plot over here as a function of the self-interaction of the mesons. So we have the chemical potential of the phase transition as a function of this key over here, which controls the self-interaction. And again, we see that at lower key, the impact of the magnetic field is a bit more important than at higher key. And the reason is the same, because of the lower lower density of the phase transition. And in this paper, we have also made a calculation of how the latent heat would change with the magnetic fields. And the answer is it would not change very much. We can see that the curves are almost constant. And we have done this because the latent heat is really important, because it may solve the problem of the energy supply of early, let's say, young gamma ray bursts. So what I mean by this is that the energy to the gamma ray bursts are usually of unknown origin, and it might be because of the latent heat released in the phase transition. Okay, so we have seen that these compact stars have some of the most extreme magnetic fields in the universe, and they are responsible for accelerating particles in the magnetosphere. And because of that, we can detect the radiation and get some information about the energy levels of the electrons and the magnetic fields of that star. We have seen that the X-ray pulsars can have periods limited because of the crust of the neutron star. So that's a really interesting point. And also the magnetic fields can modify the neutron star structure, the phase transition points, and a lot more other properties that I could not talk about, because honestly, it was just not my area of expertise and I didn't feel comfortable with that. So thank you guys for your time. I hope you can take something today.
Thank you very much, Mateus. Can you hear me?
Yes.
So thank you very much for the very nice presentation. Now we have a few questions already, so please, Christian.
No. Christian, no.
No, Chris was first. I mean,
Just quick question. It's a quick question and we
no,
have.
so Alejandro,
I raised my hand
let's
first.
leave.
No, it's Enrique,
Okay.
but we sorry, just a quick question. So I wanted to clarify, what do you mean by a chaotic magnetic field in this context? Can you explain a little bit that definition?
I'm sorry, can you
I have the
repeat?
question too.
Chaotic.
My question is, what do you define as a chaotic magnetic field in this context?
Okay. A chaotic magnetic field in
Yes.
this context would be, well, how do I say this? Well, the approximation is that it says that we can calculate the pressure, not as the parallel and perpendicular pressure, but as an isotropic pressure. So we use the equations from the relativistic mean fields without the magnetic fields, and we include the magnetic fields with a term as b squared divided by 6. So we have a single pressure, and the physical picture is that at the very small scales, the particles, they move without, let's say, without direction. So they don't move, say, with spinning. They don't move around a certain point. They move in a very chaotic manner, like a Brownian motion, I would say. And because of that, we can make this approximation of the isotropic pressure. So I would call this approximation actually isotropic pressure approximation in magnetic fields, not chaos.
Let me rephrase my question. Is this equivalent to assume that the magnetic field, that the particles feel or experience is not really uniform, but has actually fluctuations depending on the directions towards they move? This is what you mean by chaotic?
Yeah, perfect.
Okay. So that's what I wanted to make clear. Thank you.
Okay, thank you.
Just to continue the question, so but it's a function of the angle or of the radius of every, a function of both.
The magnetic fields?
Yeah.
No, we take it as a constant. So we assume it's a constant magnetic fields.
Okay.
Yeah.
But it points in random directions.
Yes, exactly.
Okay. Okay, Christian.
That was one of my questions. Indeed, if you assume that the magnetic field is points in one direction, so what you claim of chaotic is that it's an average, or you mix it different uniform magnetic fields.
Yes, it's an average over directions. It's an average.
Okay. No, I have another question. Because you can estimate the magnetic field of a surface in the surface of a compact star because of the dipole model.
Yes.
But how can you do it in the inside the neutron star? Because you always estimate about 10 to the 18 MeV. This is big. I think it's bigger than the surface. So how do you assume or expect that the magnetic field has such amount of intensity and why and how?
Okay. So I think if you take a simple dipole model, you can estimate it because the magnetic fields would decay as 1 over r. So if you have the radius and you have the value at the surface, you can estimate it in the center as well. But of course, this is a very simple response. This is not what people usually do. Honestly, I'm not an expert in this area, so my answer is certainly not going to be satisfactory. But I know that people model the evolution of the magnetic field throughout the star by solving completely the coupled Maxwell and Einstein equations. So by assuming a certain magnetic field in the center of the star, so over here in this work that we did, for example, this one, what people did was assume a certain magnetic field at the center of the star, so usually 10 to the 18 Gauss, and then the solution of the Maxwell and Einstein equations is going to give a profile inside the star, and they are going to see that the surface magnetic field is going to match the measured value. So this is one of the ways that I can think of, but there are certainly many more, let's say, advanced ways to do this.
And such models considers some specific shape of the magnetic field, not uniform.
Honestly, I would not know.
But it's the uniform constant magnetic field enough to I say, because almost everybody here uses the uniform constant magnetic field. So
yeah.
So I suppose that it's always a good approximation for the beginning. Can I a last question?
Sure.
The model you use, the quark hardware model. You so if I understand, you couple the quarks with the omega meson.
Yes.
That's right.
Yes.
Why is this? Why this meson only and not I don't know sigma rho or all the
Yeah,
standards?
that's a great question, actually. And I think there should be other mesons, because we don't expect to find just one meson coupled to the quarks. Indeed, I think in a, let's say, a better model would definitely have the sigma meson as well. But people have made this model before, and I think it was because of the repulsion of the quarks, they were able to reproduce the newly measured neutron star, which has 2.3 solar masses, if I'm not mistaken. So because of this repulsion of the quarks, there was a new parameterization for the nuclear mean fields model. And by using this quark model in conjunction with this new parameterization, they were able to reproduce this new star, this newly measured star, the mass of the star, with a quark core. So they have used this repulsive quark coupling to reproduce this star, but I think there should be also a sigma meson, a whole meson, all of this.
So you said the omega do the job and the other one.
Yes, exactly.
Okay. Okay, thanks.
Sure.
Mateus.
Thank you.
Any more questions? I have another question. So,
Sure.
this impurity parameter you told.
Oh, sorry.
Okay. So what exactly? I mean, physically, what is this? What is this parameter representing physically?
Physically, the impurity parameter represents the charge distribution that we have in the crust. So it's basically it's the difference between the number charge. So we sum over all the charges that we have in the system, and it's the difference. It's the how do you say, o desvio padrão, the standard deviation of the proton number. That's what the impurity parameter represents. So if we have a lot of different nucleons with different proton charges, we are going to have a very large impurity parameter. And if all nucleons are the same, if we have an ideal periodic lattice with just a single type of nuclei, then the impurity parameter is going to be 0 because everything is identical. So the more different our system is, the bigger is going to be this impurity parameter.
And it's in scalar. I mean, it doesn't matter the distribution of this impurity, just take an average, and that's what it uses. Okay.
Yes. So in this picture over here, maybe that's why you're asking about if it's a scalar, because we have this Zx, Zy, and Zz over here. This is because we were considering this impurity parameter with the pasta. So the pasta is anisotropic. So we had to define an effective proton number depending on the direction an electron would scatter with the pasta. So if it would come perpendicular to a cylinder, for example, it would see a different charge than if it came parallel. So it finds these effective proton numbers.
Okay, and I think the previous slide, the one before this one.
Okay.
Yeah, I mean, because you estimate the difference, I mean, the different curves changing the impurity parameter, you said, right?
Yes.
But here, they or you or whoever didn't consider this other, I mean, higher orders in the dipole and quadrupole approximations for the, or it doesn't.
For the magnetic field of the star.
Yeah. Or it doesn't make
sense. I think you're right, Sarah.
It could be, I mean, it could be like the first thing I would think to improve the approach. So
yeah, I think you're correct, but it's not my work. It's Bones, Vigano, and here. But, but I think you might be right.
Okay, and this is not, it hasn't been done.
Not that I know of.
Okay, Ricardo.
Hi, thanks for your talk. You are interested in the role of the baryons in magnetars, right?
Yes.
So I was looking at the parameters that you use in that PRC, and there are values for the magnetic anomalous moment for the baryons sitting there. Looking at the PDG, that I would like to know how the impact of these anomalous magnetic moment in your results.
Actually, they did not change a lot our results. So in the parts of the magnetic fields, we did not consider these magnetic moments. And this is because we fit the non-magnetic equation of states to make this profile. So we input the non-magnetic equation of states, and then we get the profile from the Einstein-Maxwell equation solution. But in this picture below over here, we studied how the magnetic moment alters the structure of the neutron star. So the full curves over here are those with the magnetic moments, and then the dashed curves are without magnetic moments, just with the magnetic fields. And the overall trend is just a small difference in the density of the particles, and the deltas are the most affected ones because they are going to have, well, the delta plus plus, for example, has 2 times the charge of the proton, so it's very affected. And they also have a spin of 3. So when you calculate the Landau level of the deltas, it's going to make a larger impact because of this spin that's coupled to the magnetic moments. So to rephrase this, I mean that the spin is directly coupled to the magnetic moments, and the deltas have spin 3/2, not 1/2 like the other particles. So when you couple the magnetic moments to the deltas, they're going to be more impactful. So you see that the delta minus, for example, diminishes. It appears a bit earlier when you include its magnetic moments. Yeah, so it's not a big change.
But there is a strong approximation sitting there. That table is for magnetic anomalous moment evaluating the vacuum. To be self-consistent, these kappas needs to be evaluated with the medium corrections like density and B, right? These results can change a lot if you do the evaluation self-consistent.
Yes, for sure.
And I'm not saying that's trivial evaluating that kappa, but
no, I agree with you.
Approximation sitting there. You're using the vacuum values for the kappas, right?
Yeah, and it will be a great work to be done.
Okay. Can I have a second question, Anna, please?
Yes, of course.
Thank you. When you're talking about the putting or not including beta equilibrium in our description there, when we do the equalize the pressures, when you're looking for the transition, you talk about anisotropies, and your magnetic field is around 10 to 18 Gauss. In NJL, we can see that there is no anisotropy for these fields. It's a feature of MIT bag model,
if I recall correctly, I just
saying that you can
mentioned.
see anisotropies in the perpendicular pressure compared to the parallel pressure for insane higher magnetic fields, 10 to 19 Gauss. But you are working with 10 to 18, right?
Yes, but they will always be different, right? Because even the inclusion of the magnetic field is going to have a different sign in the parallel and in the perpendicular components.
So you have
the parallel pressure is always going to be higher than the perpendicular one, right?
In NGL, there is no anisotropy for these fields. Usually these models are not so different, right? This was, I was curious about, you talking about anisotropies for 10 to 18 Gauss.
Okay. I remember I made this plot. It was a while ago when we were starting this work, and there was I don't remember the order of magnitudes, but it was a reasonable difference. But maybe I can look into this better. But even if the difference is not huge, it's not going to be exactly equal, right? So defining the pointing of the transition would still be ambiguous. And even from a theoretical point of view, even if the numerical values are approximately equal, theoretically, it would not be justified to use one or the other, I think, over the other.
Sorry, I think that it is in NGL and other models. It has to do with the definition of the pressure as a component of the energy momentum tensor. So when you have magnetic fields, there is a correction to one of the directions up to b squared.
There are people that consider this b square for pi, and there are people that do not consider this one. But numerically, if you consider this one, it will be dominating numerically this b squared there.
Okay.
Okay, thank you.
Sure. I recall that there is a difference. So the difference between the parallel and the perpendicular pressures are a term proportional to the magnetization multiplied by the magnetic fields. And the magnetization is not negligible in these magnetic fields.
It's really small, right?
Yeah,
it's
really small, but it's not. Yeah, it's small.
And in NGL, we do the calculation, and anisotropy appears only for fields around 10 to 19 Gauss, not 18. 18 is, but can be a feature of MIT bag model. I don't know. I never worked with this model.
Yeah. I would have to look into it.
Okay,
but I remember that I did this for the quark phase, for the hadron phase, I mean, and there was a difference.
Okay, so any more questions? No? So if not, let's thank Mateus again.
Okay, thank you guys.
We have a comment here. 5 times 10 to 18 Gauss, you see something in any model. Veronica said. Do you want to comment, Veronica? No. Okay, so that's all. So she said that at this intensity of field, you can see something in any model. Okay, so I stop recording now.
Okay, thanks for the opportunity, guys.
Well, thank you very much for the very nice seminar.
Of course.